Good afternoon, everyone. I'm Yu-Huai from University of Science and Technology of China, Jian-Wei Group. I'm glad to be here to make my presentation about our experiment of measurement device-independent quantum key distribution with nearly 20 kilometers of free space channel. In 1984, Professor Charles Bennett and Gilles Prasad proposed the first QKD protocol. There is no need for me to emphasize here that how important this work is. From then on, especially during the recent 20 years, quantum cryptography experienced high-speed development, both theoretically and experimentally. There are two main landmarks during the development of practical QKD that dramatically increased the security and key rate. The first one is decoy state method. With this technology, the photon number split attack is completely immune in practical QKD system, with coherent light as the photon source. Thus, the security distance for real-world QKD can exceed 100 kilometers, and the requirement of perfect single-photon source is then removed. Later in 2012, to beat the various kinds of attacks that against the measurement devices, Professor Huai proposed MDI-QKD protocol as a time-reversed version of entanglement-based QKD. MDI-QKD is naturally immune to all attacks against the measurement. Thus, by combining these two techniques together, that decoy state MDI-QKD provides a marvelous security and key rate in realistic systems. Since then, great efforts have been taken in the development of MDI-QKD. The first experiment has soon been realized over a fiber channel of 50 kilometers just 1 year after the proposal of protocol. And soon the distance has been extended to over 400 kilometers in 2016. More practical demonstration of MDI-QKD under realistic conditions, such as QKD network, a high-speed MDI-QKD over asymmetric channels, and integrated photonics chip-based system were reported in the recent years. However, all these works were performed over fiber channels. The biggest problem for optic fibers is that the attenuation increases exponentially with distance. As an contrast, the loss of photon in long-distance free space channel is mainly caused by the diffraction of laser beam, which increases with distance squared, which is far below that of fiber channel. Thus, realizing MDI-QKD in free space is crucial for a large-scale quantum network. On the other hand, free space channel is also more flexible to deploy, thus is an important reinforcement to fiber channel for practical QKD applications. However, the free space channel has its own problems that makes the MDI-QKD difficult to be realized. As we can see, the heart of the MDI-QKD is realizing ornamental interference between independent photons or coherent pulses with high visibility. To achieve this, the photons or coherent pulses should be identical in all degrees of freedom that not being used as encoding. That includes spatial, spectral, temporal, polarization, and so on. All these degrees are much easier to be maintained, locked or calibrated by fiber channels, but quite difficult in free space. Firstly, the atmospheric turbulence makes things complicated in free space channel. The temperature and the density of air changes in different places and different time in free space channel. Thus, when a Gaussian beam transmitted through the channel, it experiences different refractive indices in different parts and different time. This results in a varying and randomly distributed wavefront at the receiver. In other words, the spatial coherence of the laser beam is disturbed, introducing beam wandering, mode expanding, and phase singularity. As an example, the far-field distribution of a nice Gaussian beam is a small spot that's recorded by a CCD, like this. However, after propagating through a disturbed atmospheric channel, the far-field distribution is expanded with randomly distributed patterns. Obviously, this beam is not possible to be directly used for horizontal interference. Here, to guarantee the spatial mode indistinguishability between independent photon sources that transmitted through different atmospheric channels, we applied a straightforward method, that is, to coupling the received photons into single-mode fibers. This method places a spatial mode filtering that's only post-selecting the basic mode. This brings new problems that the coupling efficiency is normally very low with strong fluctuation, which is the first challenge we face in this experiment. Here we introduce the technique of adaptive optics without wavefront sensor to overcome the challenge. Traditionally, the wavefront of a laser beam is detected by a Hartmann detector in an adaptive optic system. However, under strong turbulence, it is difficult to effectively estimate wavefront due to intensities, scintillations, and phase singularities. Therefore, an adaptive optic system without wavefront sensors is desired. Here, a laser with wavelength of 1570 nanometers was emitted and transmitted at the same channel with the 1550 quantum signal laser as a probe for channel efficiency. The probe laser can be regarded as experienced the same atmospheric turbulence with the signal laser, they both being reflected by a deformable mirror, which can change the surface to compensate the disturbed wavefront. After having been coupled into single-mode fibers, the intensity of probe laser is measured. A stochastic parallel gradient descent algorithm is performed here to optimizing the intensity of probe laser by changing the surface of the deformable mirror at real time. By this, the coupling efficiency of signal pulses will also optimized. The closed-loop bandwidth of this adaptive optic system is about 500 Hz, which is far above the typical frequency of atmospheric turbulence. An increment of 3 to 6 dB of the signal mode fiber coupling efficiency is achieved with the adaptive optic system. So a total increment of about 6 to 12 dB is achieved for all two free space channels. We may take a look at the histogram, which is the probability distribution of different channel efficiencies. Except the increase of the average efficiency, the deviation is also significantly reduced. This means that the arrival signal pulses are more likely to have the similar intensity, which is good for a high visibility of interference. Finally, with the adaptive optic systems, the total channel efficiency is increased from about 48 dB to about 40 dB in our double 10 kilometer order of free space channels. The time synchronization of independent clocks and the frequency calibration of independent lasers are other two challenges for free space MDI-QKD. Technicals used in fiber-based systems unfortunately cannot be directly applied. Most previous fiber-based MDI-QKD systems share master clock signal via additional fiber channels to provide a common clock for each source, or share a laser between encoding nodes for the locking of laser frequencies. However, the atmospheric turbulence makes it difficult to recover the transmitted clock signal, and it is also not likely to build an independent channel to share laser frequency that have high isolation with the encoded signal. Here, we use ultra-stable crystal oscillators as local clocks to maintain the time reference independently between different terminals. The crystal oscillators have good short-term stability. At the Maimaiti terminal Charlie, about 10% of arrival photons was split in to be directly measured by single photon detectors. The arrival times were recorded to estimate the residual time drift between Alice and Charlie or Bob and Charlie. Once calibrated, the frequency difference between different clocks can be guaranteed to be low enough that the residual time drift is normally below 1 picosecond per second. This can be easily compensated by controlling time management boards every few seconds to maintain the synchronization of time references between all three terminals. Finally, the deviation of the pulse arrival time difference is measured to be about 32 picoseconds. Laser emitted from commercial DFB laser can achieve fairly good frequency stability below 10 MHz with well-controlled temperature. Combine this with our time synchronization of tens of picoseconds to achieve excellent interference visibility. The remaining challenge is to calibrate the central frequency of independent DFB lasers without a shared reference. It can be done by choosing spectral lines of atoms or molecules as independent references. Here, we choose the spectral line of 1550.52 nanometers of HCN molecule. The power of laser that passing or not passing the HCN gas cell were measured to estimate the absorption rate. By turning the temperature of laser cavity, the laser frequency, that the absorption rate is changed. Finally, the laser frequency was locked in the spectral line with an accuracy better than 10 MHz. So the product of time synchronization derivation and laser frequency difference derivation is far below 1 divided 4 pi, makes it possible to achieve a good Hong-Mandel interference visibility. The last 1 degree of freedom to be considered is polarization. Here, we use fiber PBS to ensure the polarization indistinguishability, and use polarization controller to ensure the split ratio for interference and for arrival time measurement. Thus, the unstable of polarization in channel can only slightly disturb the channel efficiency of interference photons, however not affect the polarization indistinguishability. Based on this technique mentioned above, we implement long-distance free space Hong-Mandel interference and MDI-QKD in intracity channels. Alice and Charlie are 7.7 kilometers apart. Bob and Charlie are 11.5 kilometers apart. Alice and Bob are in opposite directions from Charlie. Thus, the total distance between Alice and Bob is 19.2 kilometers. We performed the system for over 13 hours, and a final secure key rate of 6.11 bps is achieved with the consideration of finite size key effect. Here shows the result of Hong-Mandel interference. The pulse repetition rate is 100 MHz in our system. Thus, with a digital delay in the time digital converter, the coincidence peak appears every 10 nanoseconds. A visibility of 0.412 is directly observed, showing as the gray bars. Here, we applied a post-selection method to further increase the visibility. Since we have a 1570 nanometer probe laser to perform the adaptive optic system, it can also be used to estimate real-time channel efficiencies. Thus, we are able to know the intensity difference between each pair of signal pulses. If we only post-select the pairs of signal pulses that have similar intensities, the visibility of Hong-Mandel can be significantly increased. As the green bar shows, with a post-selection threshold of 0.8, the visibility is increased to 0.474. Here are the details of MDI-QKD. We used the asymmetric 4-intensity decoy state MDI-QKD protocol with time-bin encoding. Z bases are encoded by time-bin 0 or time-bin 1. X bases are encoded by 0 or pi relative phases between the two time-bins. The optimized parameters are calculated beforehand as listed in this table, and the QBER are shown in the histogram. The final key rate without post-selection as the triangle spot is slightly departure from the expected curve. However, with the post-selecting method, the Hong-Mandel the visibility is increased. Thus, the key rate can be well fitted with the theoretical curve as the solid black circle. So, with the complete of free space MDI-QKD, we have taken the first step towards satellite-based MDI-QKD. The topological structure of satellite-assisted MDI network is flexible. Here are some examples. The satellite can be a server node connecting different ground stations or a client node connecting our user nodes with ground stations. Also, inter-satellite connection is useful to extend the network to large scale. With fast-moving satellites, new challenges have been introduced, such as the laser frequency will be affected by the Doppler frequency shift, and at the order of several gigahertz. The arrival time will also be rapidly changing due to the variation of distances between different terminals that need to be predicted and compensated. Overcoming this technical challenge will be the next goal for us. On the other hand, the technical developed in this work, such as independent clock synchronization and independent laser frequency locking, can be directly applied into fiber-based MDI-QKD systems that can significantly simplify the complexity and enhance the robustness. Moreover, as the detection in MDI-QKD is twofold coincidence measurement, it has a natural advantage that can work at a much higher noise comparing to BB84 protocol, which is very important for full-time availability for free space applications. And our work also opens the possibility of more complex quantum information process at large scale, such as quantum entanglement swapping, twin field QKD, and testing the interface of quantum mechanics and general relativity. Thank you.